Okay, so here we go. We'll continue with another episode of this GCP reliable cloud infrastructure design and process. In the previous video, we arrived here at designing reliable system. This module will be, it's clear what will be about and will be only theoretical.
In this module, we talk about how to design reliable systems. Specifically, we'll go over how to design services to meet requirements for availability, durability, and scalability. We will also discuss how to implement fault-tolerant systems by avoiding single points of failure, correlated failures, and cascading failures. Overload can also be a challenge in distributed systems, and we will see how to avoid overload failures by using design patterns such as a circuit breaker and truncated exponential backoff. How to design resilient data storage systems with lazy deletion is introduced. When things go wrong, we want our system to stay in control, so we discuss design decisions for different operational states including normal, degraded, and failure scenarios. Finally, we cover how to analyze disaster scenarios and plan, implement, and test for disaster recovery. Let's start by considering the key performance metrics for reliable systems. When designing for reliability, consider availability, durability, and scalability as the key performance metrics. Let me explain each of these. Availability is the percent of time a system is running and able to process requests. To achieve high availability, monitoring is vital. Health checks can detect when an application reports that it is okay. More detailed monitoring of services using white box metrics to count traffic successes and failures will help predict problems. Building in fault tolerance by, for example, removing single points of failure is also vital for improving availability. Backup systems also play a key role in improving availability. Durability is the chance of losing data because hardware or system failure. Ensuring that data is preserved and available is a mixture of replication and backup. Data can be replicated in multiple zones. Regular restores from backup should be performed to confirm that the process works as expected. Scalability is the ability of a system to continue to work as user load and data grow. Monitoring and auto-scaling should be used to respond to variations in load. The metrics for scaling can be the standard metrics like CPU or memory, or you can create custom metrics like number of players on a game server.
Okay, nice. I like this schema.
Ensuring that data is preserved and available is
So reliability can be decomposed in availability, durability, and scalability. The system is reliable in time, I would say. Yeah, they're all kind of function of time in some way. Therefore, varying the number of requests, the availability is to be checked as the health of the system. We can improve it using backup systems and using with fault tolerance design. Okay, the durability is more related to the storage, and the scalability is related to the amount of data available in the network, in the system. Okay. Hey, why it's not loading the next activity?
Now that we've covered the key performance metrics, let's design for complete rack fit.
Okay.
Now that we've covered the key performance metrics, let's design for reliability. Avoid single points of failure by replicating data and creating multiple virtual machine instances. It is important to define your unit of deployment and understand its capabilities. To avoid single points of failure, you should deploy 2 extra instances, or n+2, to handle both failure and upgrades. These deployments should ideally be in different zones to mitigate for zonal failures. Let me explain the upgrade consideration. Consider 3 VMs that are load balanced to achieve n+2. If one is being upgraded and another fails, 50% of the available capacity of the compute is removed, which potentially doubles the load on the remaining instance and increases the chances of that failing. This is where capacity planning and knowing the capability of your deployment unit is important. Also, for ease of scaling, it is a good practice to make the deployment units interchangeable stateless clones. It is also important to be aware of correlated failures. These occur when related items fail at the same time. At the simplest level, if a single machine fails, all requests served by that machine fail. At a hardware level, if a top-of-rack switch fails, the complete rack fails. At the cloud level, if a zone or region is lost, all the resources are unavailable. Servers running the same software suffer from the same issue. If there is a fault in the software, the servers may fail at a similar time. Correlated failures can also apply to configuration data. If a global configuration system fails and multiple systems depend on it, they potentially fail too. When we have a group of related items that could fail together, we refer to it as a failure or fault domain. Several techniques can be used to avoid correlated failures. It is useful to be aware of failure domains. Then servers can be decoupled using microservices distributed among multiple failure domains. To achieve this, you can divide business logic into services based on failure domains and deploy to multiple zones and/or regions. At a finer level of granularity, it is good to split responsibilities into components and spread these over multiple processes. This way, a failure in one component will not affect other components. If all responsibilities are in one component, a failure in one responsibility has a high likelihood of causing all responsibilities to fail. When you design microservices, your design should result in loosely coupled, independent but collaborating services. A failure in one service should not cause a failure in another service. It may cause a collaborating service to have reduced capacity or not be able to fully process its workflows, but the collaborating service remains in control and does not fail.
Okay.
Cascading failures occur when one system fails, causing others to be overloaded and subsequently fail. For example, a message queue could be overloaded because a backend fails and it cannot process messages placed on the queue. The graphic on the left shows a cloud load balancer distributing load across two backend servers. Each server can handle a maximum of 1,000 queries per second. The load balancer is currently sending 600 queries per second to each instance. If server B now fails, all 1,200 queries per second have to be sent to just server A, as shown on the right. This is much higher than the specified maximum and could lead to cascading failure. So, how do we avoid cascading failures? Cascading failures can be handled with support from the deployment platform. For example, you can use health checks in Compute Engine or readiness and liveliness probes in GKE to enable the detection and repair of unhealthy instances. You want to ensure that new instances start fast and ideally do not rely on other backends or systems to start up before they are ready. The graphic on this slide illustrates a deployment with 4 servers behind a load balancer. Based on the current traffic, a server failure can be absorbed by the remaining 3 servers, as shown on the right-hand side. If the system uses Compute Engine with instance groups and auto-healing, the failed server would be replaced with a new instance. As I just mentioned, it's important for that new server to start up quickly to restore full capacity as quickly as possible. Also, this setup only works for stateless services. You also want to plan against query of death, where a request made to a service causes a failure in the service. This is referred to as a query of death because the error manifests itself as overconsumption of resources, but in reality is due to an error in the business logic itself. This can be difficult to diagnose and requires good monitoring, observability, and logging to determine the root cause of the problem. When the requests are made, latency, resource utilization, and error rates should be monitored to help identify the problem. You should also plan against positive feedback cycle overload failure, where a problem is caused by trying to prevent problems. This happens when you try to make the system more reliable by adding retries in the event of a failure. Instead of fixing the failure, this creates the potential for overload. You may actually be adding more load to an already overloaded system. The solution is intelligent retries that make use of feedback from the service that is failing. Let me discuss 2 strategies to address this. If a service fails, it is okay to try again. However, this must be done in a controlled manner. One way to use the exponential backup pattern. This performs a retry, but not immediately. You should wait between retry attempts, waiting a little longer each time a request fails, therefore giving the failing service time to recover. The number of retries should be limited to a maximum, and the length of time before giving up should also be limited. As an example, consider a failed request to a service. Using exponential backoff, we may wait 1 second plus a random number of milliseconds and try again. If the request fails again, we wait 2 seconds plus a random number of milliseconds and try again. Fail again, then wait 4 seconds plus a random number of milliseconds before retrying and continue until a maximum limit is reached. The circuit breaker pattern can also protect a service from too many retries. The pattern implements a solution for when a service is in a degraded state of operation. It is important because if a service is down or overloaded and all its clients are retrying, the extra requests actually make matters worse. The circuit breaker design pattern protects the service behind a proxy that monitors the service health. If the service is not deemed healthy by the circuit breaker, it will not forward requests to the service. When the service becomes operational again, the circuit breaker will begin feeding requests to it again in a controlled manner. If you are using GKE, the Istio service mesh automatically implements circuit breakers. Lazy deletion is a method that builds in the ability to reliably recover data when a user deletes the data by mistake. With lazy deletion, a deletion pipeline similar to that shown in this graphic is initiated, and the deletion progresses in phases. The first stage is that the user deletes the data, but it can be restored within a predefined time period. In this example, it's 30 days. This protects against mistakes by the user. When the predefined period is over, the data is no longer visible to the user, but moves to the soft deletion phase. Here, the data can be restored by user support or administrators. This deletion protects against any mistakes in the application. After the soft deletion period of 15, 30, 45, or even 50 days, the data is deleted and no longer available. The only way to restore the data is by whatever backups or archives were made of the data.
Okay, now we have an activity. Therefore, I will need my notes to open my workbook. Okay.
In this design activity, you draw a diagram that depicts how you can deploy your application for high availability, scalability, and durability. Let me show you an example of what to draw. This diagram is for an online bank application with customers in the United States. I want the web UI to be highly available, so here I depict it as being deployed behind a global external application load balancer across multiple regions and multiple zones within each region. I choose US Central 1 as the main region because it's somewhere in the middle of the US. I also have a backup region in US East 1, which is on the east coast of the US. I deploy the accounts and product services as backends to just the US Central 1 region, but I'm using multiple zones, US Central 1A and US Central 1B for high availability. I even have a failover Cloud SQL database. The Firestore database for the product service is multi-regional, so I don't need to worry about a failover. In case of a disaster, I'll keep backups in a multi-regional cloud storage bucket. That way, if there's a regional outage, I can restore in another region. Refer to Activity 10 in your workbook to create a similar diagram for your...
Okay, so I'm curious. I don't recall doing activity 9. Oh yeah, I did it. It was the diagramming your network. Okay, therefore design reliable scalable applications. We'll just copy this and do an example here. So through HTTPS with a global application load balancer, Europe West 1, and I'm not sure if it does exist this. However, West 1, okay. So now this will be Europe West 1A. If I'm not wrong, this should be something in Belgium. God. Okay, and why was this? Yeah, whatever. This will be B. Okay, so we have a failover region. However, I'm not sure if this can be really necessary, as my service will not be mission critical. I don't care if, I mean, not really. In reality, I care if they cannot access the service. Therefore, a regional double zone will be used. And yeah, then we put this here, this here. So proxy load balancer, this is for a banking system. In our case, I think it will not be necessary. As in our case, things are simpler. We just have this UE front end. The front end, well, maybe underneath we'll use a proxy network load balancer. Who knows? Yeah, not sure. It depends on the service you use, maybe. Then we have the itinerary definition service. Interview service, and it says the analytics service, the customer itinerary interview, and yeah, the analytics. Okay, so here we'll have inventory itinerary. Oh my god, don't tell me I did it here. Yeah, as always. Okay, therefore we'll also have, so we'll have availability both for the front end and the back end. Then we'll have durability and scalability. Well, this is scalable because the backends services yeah, let's see. I did not choose how to deploy the application. Yeah, as they are really simple, loosely coupled services, they will not be containers. They will be run on Cloud Run function or application. Maybe the application, not sure. Of course, the one that takes less money to use them. Therefore, the scalability is easy, as in the case of, especially in the case of cloud application, it can scale, auto scale. Let me see just one thing. So in GCP, what are the auto scaling options when deploying on Cloud Run functions and App Engine? Okay. Okay. Nice, okay. Therefore, we have many options on how to scale up. Nice. Therefore, we can continue, but before, I will just change the color of this to yellow, as we need to remember that we did an exercise here. Mark as completed. And let's continue this.
In this activity, you are asked to draw a diagram that depicts how your application can be deployed for high availability, scalability, and durability. For our online travel application, ClickTravel, I'm assuming that this is an American company, but that I have a large group of customers in Europe. I want the UI to be highly available, so I've placed it into US Central 1 and Europe West 2 behind a global external application load balancer. This load balancer will send user requests to the region closest to the user, unless that region cannot handle the traffic. I could also deploy the backends globally, but I'm trying to optimize cost. I could start by just deploying those in US Central 1. This will create latency for our European users, but I can always revisit this later and have a similar backend in Europe West 2. To ensure high availability, I've decided to deploy the orders and inventory services to multiple zones. Because the analytics service is not customer facing, I can save some money by deploying it to a single zone. I again have a failover Cloud SQL database, and the Firestore database and BigQuery data warehouse are multi-regional, so I don't need to worry about a failover for those. In case of a disaster, I'll keep backups in a multi-regional cloud storage bucket. That way, if there's a regional outage, I can restore in another region.
Nice. So that's simple. Now we'll have a look at disaster recovery plans.
Now that we've designed for reliability, let's explore disaster planning. High availability can be achieved by deploying to multiple zones in a region. When using Compute Engine, for higher availability, you can use a regional instance group, which provides built-in functionality to keep instances running. Use auto-healing with an application health check and load balancing to distribute load. For data, the storage solution selected will affect what is needed to achieve high availability.
Just a second, there's a friend waiting outside who wants to participate. I will let him in. Hello. Introduce you. Silver Domingo. Let's go. He will be with us here, supervising.
Now that we've designed for reliability, let's explore disaster planning. High availability can be achieved by deploying to multiple zones in a region. When using Compute Engine, for higher availability, you can use a regional instance group, which provides built-in functionality to keep instances running. Use auto-healing with an application health check and load balancing to distribute load. For data, the storage solution selected will affect what is needed to achieve high availability. For Cloud SQL, the database can be configured for high availability, which provides data redundancy and a standby instance of the database server in another zone. This diagram shows a high availability configuration with a regional managed instance group for a web application that's behind a load balancer. The master Cloud SQL instance is in US Central 1A, with a replica instance in US Central 1F. Some data services, such as Firestore or Spanner, provide high availability by default. In the previous example, the regional managed instance group distributes VMs across zones. You can choose between single zones and multiple zones or regional configurations when creating your instance group, as you can see in this screenshot. Google Kubernetes Engine clusters can also be deployed to either a single or multiple zones, as shown in this screenshot. A cluster consists of a master controller and collections of node pools. Regional clusters increase the availability of both a cluster's master and its nodes by replicating them across multiple zones of a region. If you are using instance groups for your service, you should create a health check to enable auto-healing. The health check is a test endpoint in your service. It should indicate that your service is available and ready to accept requests, and not just that the server is running. The challenge with creating a good health check endpoint is that if you use other backend services, you need to check that they are available to provide positive confirmation that your service is ready to run. If the services it is dependent on are not available, it should not be available. If a health check fails the instance group, it will remove the failing instance and create a new one. Health checks can also be used by load balancers to determine which instances to send requests to. let's go over how to achieve high availability for Google Cloud's data storage and database services. For Google Cloud Storage, you can achieve high availability with multi-region storage buckets if the latency impact is negligible. As this table illustrates, the multi-region availability benefit is a factor of 2 as the unavailability decreases from 0.1% to 0.05%. If you are using Cloud SQL and need high availability, you can create a failover replica. This graphic shows the configuration where a master is configured in one zone and a replica is created in another zone but in the same region. If the master is unavailable, the failover will automatically be switched to take over the master. Remember that you are paying for the extra instance with this design. Firestore and Spanner both offer single and multi-region deployments. A multi-region location is a general geographical area, such as the United States. Data in a multi-region location is replicated in multiple regions. Within a region, data is replicated across zones. Multi-region locations can withstand the loss of entire regions and maintain availability without losing data. The multi-region configurations for both Firestore and Spanner offer 5 nines of availability, which is less than 6 minutes of downtime per year. Now, I already mentioned that deploying for high availability increases cost because extra resources are used. It is important that you consider the costs of your architectural decisions as part of your design process. Don't just estimate the cost of the resources used, but also consider the cost of your service being down. This table shown is a really effective way of assessing the risk versus cost by considering the different deployment options and balancing them against the cost of being down. Now, let me introduce some disaster recovery strategies. A simple disaster recovery strategy may be to have a cold standby. You should create snapshots of persistent disks, machine images, and data backups and store them in a multi-region storage. This diagram shows a simple system using this strategy. Snapshots are taken that can be used to recreate the system. If the main region fails, you can spin up servers in the backup region using the snapshot images and persistent disks. You will have to route requests to the new region, and it's vital to document and test this recovery procedure regularly. Another disaster recovery strategy is to have a hot standby where instance groups exist in multiple regions, and traffic is forwarded with a global load balancer. This diagram shows such a configuration. I already mentioned this, but you can also implement this for data storage services like multi-regional cloud storage buckets and database services like Spanner and Firestore. Now, any disaster recovery plan should consider its aims in terms of 2 metrics, the recovery point objective and the recovery time objective. The recovery point objective is the amount of data that would be acceptable to lose, and the recovery time objective is how long it can take to be back up and running. You should brainstorm scenarios that might cause data loss or service failures and build a table similar to the one shown here. This can be helpful to provide structure on the different scenarios and to prioritize them accordingly. You will create a table like this in the upcoming design activity along with the recovery plan. You should create a plan for how to recover based on the disaster scenarios that you define. For each scenario, devise a strategy based on the risk and recovery point and time objectives. This isn't something that you want to simply document and leave. You should communicate the process for recovering from failures to all parties. The procedure should be tested and validated regularly, at least once per year, and ideally recovery becomes a part of daily operations, which helps streamline the process. This table illustrates the backup strategy for different resources along with the location of the backups and the recovery procedure. This simplified view illustrates the type of information that you should capture. Before we get into our next design activity, I just want to emphasize how important it is to prepare a team for disaster by using drills. Have you decided what you think can go wrong with your system? Think about the plans for addressing each scenario and document these plans. Then practice these plans periodically in either a test or a production environment. At each stage, assess the risks carefully and balance the cost of availability against the cost of unavailability. The cost of unavailability will help you evaluate the risk of not knowing the system's weaknesses.
Okay.
In this design activity, you brainstorm disaster scenarios for your case study and formulate a disaster recovery plan. Here's an example of such a brainstorming activity. The purpose of this activity is to think of disaster scenarios and assess how severely they would impact your services. The recovery point objective represents the maximum amount of data you would be willing to lose. Obviously, this would be different for your orders database, where you wouldn't want to lose any data, and your products rating database, where you could tolerate some loss. The recovery time objective represents how long it would take to recover from a disaster. In this example, we are estimating that we could recover our product rating service database from a backup in an hour, and our order service within 2 minutes. Now, like all things in life, we should prioritize. There's never time to get everything done, so work on the highest priority items first. Once you've identified these scenarios, come up with plans for recovery. These plans will be different based on your recovery point and recovery time objectives, as well as the priorities. In this example, performing daily backups of our ratings database is good enough to meet our objectives. For the orders database, that won't be adequate, so we'll implement a failover replica in another zone. Refer to activities 11A, B, and C in your design workbook to document similar disaster scenarios for your case study and formulate a disaster recovery plan for each.
Okay. Therefore now we should be able to go and finish the exercises in our workbook. (11a). You've deployed for high availability by replicating resources in multiple zones. However, to meet regulatory requirements, you need a plan to recover from a disaster that brings down the entire region. The current architecture is depicted below. On the next slide, create a plan to bring up your application in another region if your main region is down. Below is an example. Okay, we just use this. Okay, so it will be EU Central 1, not sure, yeah, like West 1, EU West 1A, and EU West 1B. So here I have the itinerary, here the what was the other interview and the analytics. Here itinerary and interview. I mean, yeah, this is it basically. What else? These are not, these do not have replicas as they are multi-regional by default. Okay, so now we need this to be copied. Let's see if we have space for all of them. I think not. Yeah, in reality, yes. Programmer deleted all rating accidentally, orders table crashed. So interview form is like orders for us. So database crashes. Yeah, this can't happen. 0, we can't lose data. Therefore, we need to be up in less time possible and with high priority. Instead, yeah, the itinerary definition sorry, may I ask you to keep silent, please? In this case, the itinerary definition service, maybe I can accept it to be down a bit, like even 24 hours as, and recovery time objective 1 hour, and priority medium. What's the scenario here? Programmer deleted ratings accidentally. The service is not working. Service not working. This itinerary view mode, service not working again. In this case, I cannot accept 24 hours as recovery point objective. We will not lose data because in this case, recovery point objective can be 24 hours. I mean, no less. It can be a couple hours. Recovery time objective. No, this can't be anything. This doesn't. We cannot accept this to happen. Imagine if a guy is entering there to change something in their trip. They cannot do it. I mean, they already paid it. They can wait a couple hours. And this has to happen also in 1 hour. The analytics are, I would say, the same. But here we can, I mean, we can jump even 5 days, I don't know, a couple days. And it has to be back in a couple days too. I don't care about reporting now. Let's put another color. For each scenario, fill in the table on the next slide below as an example. Interview form crash. We need daily backups, auto backups. Multi-regional cloud storage bucket. And run restore script. And then we have itinerary. So the itinerary mod view crash. So we'll have daily auto backups, multi-regional cloud storage bucket. It will be also a run restore script. Then we have itinerary definition. Yeah, okay, I mean, we have these two. It's not an extensive example, but yeah, we have it. Fuck this, okay.
In this activity, you were asked to come up with disaster recovery scenarios and plans for the case study you've been working on. Here's an example of some disaster scenarios for our online travel portal, ClickTravel. Each of our services use different database services and has different objectives and priorities. All of that affects how we design our disaster recovery plans. Our analytics service in BigQuery had the lowest priority. Therefore, we should be able to re-import data to rebuild analytics tables if a user deletes them. Our order service can't tolerate any data loss and has to be up and running almost immediately. For this, we need a failover replica in addition to binary logging and automated backups. Our inventory service uses Firestore, and for that, we can implement daily automated backups.
Okay, automated failover. I like this. This topic is not really the clearest for me. In particular, like the approach we are having to this, like the schema, the canvas we're using is kind of inconsistent for me. I will for sure need to find maybe a better way to manage all these concepts and to not forget anything, to have like a systematic way to manage this. Okay, so module quits. We need to take at least one good option. Relational database, extremely high availability. You're creating a service and you want to protect it from being overloaded by too many clients retries in the event of a partial outage. Which design pattern would you implement? You're creating a service and you want to protect it from being overloaded by too many client retries in the event of partial outage. I'm not sure about this, if it does even exist. Circuit breaker and truncated exponential backoff. Well, with exponential backoff, if I'm not wrong. However, I want to get the differences between these two. This answer is not correct because the truncated exponential backoff attempts a retry on the expectation that it is likely to succeed. This will cause problems if there is a partial outage because the retry will not succeed. Okay, so spanner And here I cannot use exponential backoff because exponential backoff is just to slow down things. Instead, the circuit breaker is when things are broken already. Partial outage. Okay, nice. This answer is correct because the circuit breaker will attempt to prevent an operation that is likely to fail, and therefore will protect the resource that is in a partial outage and hopefully prevent cascading failure.
In this module, we covered how to deploy our applications for high availability, durability, and scalability. For high availability, we can deploy our resources across multiple zones and regions. For durability, we can keep multiple copies of data and perform regular backups. And for scalability, we can deploy multiple instances of our services and set up autoscalers. We also introduced disaster recovery planning, which is defined by coming up with the scenarios that would cause you to lose data and having a plan in place for recovering if a disaster happens.
Nice, okay, so we touched these interesting
In
topics.
this module, we cover security. Google has been operating securely in the cloud for 20 years. There's a strong belief that security empowers innovation. The approach of the cloud architect should be that security should be put first. Everything else will follow from this. In this module, you will learn how to design secure systems using industry best practices. For example, when designing a secure system, you will learn how to apply the principle of least privilege and the practice of separation of concerns. Performing regular audits is also a key part of running a secure system. Leveraging Google's Security Command Center can help to identify vulnerabilities as part of your process. Also, when securing systems, governance is a major consideration. You will learn how organization policies and folders can simplify governance. Preventing access to unwanted visitors is always a challenge. Authentication and authorization is one approach and can be implemented in many different ways. You will learn how best to use IAM roles, identity-aware proxy, and identity platform. You'll also learn to manage the access and authorization of resources by machines and processes using service accounts. At a lower level of access control, you will learn how to secure network access using private IPs, firewalls, and Google Cloud Private Access. Last but not least, you'll learn how to mitigate DDoS attacks by leveraging Cloud DNS and Google Cloud Armor. As you see, there is a lot to security. Let's get started. Let's begin by talking about some security concepts and introducing some of the best practices for security design. When you move an application to Google Cloud, Google handles many of the lower layers of the overall security stack. Because of its scale, Google can deliver a higher level of security at these layers than most of its customers could afford to do on their own. This does not mean that Google is responsible for all the security aspects. Google Cloud Security is a shared responsibility between you and Google, so it is important that there is a clear separation of duties and there is no ambiguity between what is provided by the platform and what you are responsible for. For this, there needs to be transparency. There are certain actions you as a client are responsible for and some that Google is responsible for. Google Cloud provides the controls and features required to leverage the platform together with the tools to monitor your services. Google implements security in layers. At the base is custom-built hardware and servers that are loaded using a verified boot loading system. All the way through the stack, security is at the forefront. When you take your part in security, for example, establishing firewall rules or configuring IAM, as long as they are configured correctly, you have a safe environment. There are tools Google Cloud provides that can be used for monitoring and auditing your networks, which we will discuss shortly, or you can also install your own tools. Let's talk about some best practices when implementing security. The principle of least privilege is the practice of granting a user only the minimal set of permissions required to perform a duty. This should apply to machine instances and processes, as well as users. Google Cloud provides Cloud IAM to help apply this principle. You can use it to identify users with their login or identify machines using service accounts. Roles should be assigned to users and service accounts to restrict what they can do, always following the principle of least privilege. Separation of duties is another best practice, and it has two primary objectives. 1. Prevention of conflict of interest. And 2. The detection of control failures, for example, security breaches and information theft. From a practical perspective, this means that no one person can change or delete data without being detected. No one person can steal sensitive data, and no single person is in charge of designing, implementing, and reporting on sensitive systems. For example, a developer who writes the code should not be responsible for deploying that code, and anybody that has the permission to deploy should not be able to change the code. One approach to achieve this separation of duties in Google Cloud is to use multiple projects to separate duties. Different people can be given suitable rights to different projects, with these permissions following the principle of separation of duties. Folders are especially useful for organizing multiple projects. It is also vital to audit Google Cloud logs to discover attacks and potential security breaches. All Google Cloud services write to audit logs, so there is a rich source of information available. These logs include admin, data access, VPC flow, firewall, and system logs, so an in-depth view of activity is provided for audit. Now, moving to the cloud often requires maintaining compliance with regulatory requirements or guidelines. Google Cloud meets many third-party and government compliance standards worldwide. While Google Cloud has been certified as secure, for example, to ISO IEC 27001, HIPAA, and SOC 1, that does not mean your application running on Google Cloud is certified. Your concern should always be on what you build. Google Cloud also offers the Security Command Center, which provides access to organizational and project security configuration. As you can see in this screenshot, the Security Command Center provides a dashboard that reports security health analysis, threat detections, anomaly detection, and a summary report. Once a threat is detected, a set of actionable recommendations is provided. move on to talk about securing people. When granting people access to your projects, you should add them as members and assign them one or more roles. Roles are simply a list of permissions. To see what permissions are granted to roles, use the Cloud Console as shown on the right. Here you can see the role BigQuery user and the associated 15 permissions the role has assigned to it. You can assign these predefined roles to its members or customize your own roles. Now, any member added to your project will be identified by their login. For simplifying management of members and their permissions, I recommend that you create groups. That way, you just need to add members to a group, and new members automatically acquire the permissions of the group. The same applies for removing members from a group, which also removes the permissions of that group. I also recommend using organizational policies and folders to simplify securing your environments and managing your resources. Organizational policies apply to all resources underneath an organization, and Cloud IAM policies are also inherited top to bottom, as shown on the right. Folders inherit policies of the organization, projects inherit policies of the folders, and so on. I already mentioned that roles should be granted to groups, not individuals, because it simplifies management. Make sure to define groups carefully and make them more granular than job roles. It's better to use multiple groups for better control. When it comes to roles, it's better to use predefined roles over custom roles. Google has defined the roles for a reason, and it should be an exceptional case that a role does not fit your use case. When granting roles, remember the principle of least privilege. Always grant the smallest scope required. Owner and editor roles should be limited. These are not or should not be required by the majority of users. I also recommend leveraging Cloud Identity Aware Proxy, or Cloud IAP. Cloud IAP provides managed access to applications running in App Engine standard environment, App Engine flexible environment, Compute Engine, and GKE. It allows employees to securely access web-based applications deployed on Google Cloud without requiring a VPN. Administrators control who has access, and users are required to log on to gain access to the applications. The screenshots on the right show Cloud IAP being enabled on an App Engine application and the dialog for adding new members or permissions. Google Cloud also offers Identity Platform as a customer identity and access management (CIAM) platform for adding identity and access management to applications. In other words, Identity Platform provides sign-up and sign-in for end-user applications. Now, you need to select a service provider to use Identity Platform. A broad range of protocol support is available, including SAML, OpenID, email and password, phone, social, and Apple. This graphic shows a part of the configuration with a list of potential providers.
Okay. Now securing machine access, which is quite simple in the end.
We just talked about assigning roles to members. We focused on users and Google Groups, but there's another kind of member that helps secure machine access. A service account is a special kind of account used by an application, a virtual machine instance, or a GKE node pool. Applications or services use service accounts to make authorized API calls. The service account is the identity of the service and defines permissions which control the resources the service can access. A service account is both an identity and resource. A service account is used as an identity for your application or service to authenticate, for example, a Compute Engine VM running as a service account. To give the VM access to the necessary resources, you need to grant the relevant Cloud IAM roles to the service account. At the same time, you need to control who can create VMs with the service account, so random VMs cannot assume the identity. Here, the service account is a resource to be permissioned. You assign the service account user role to the users you trust to use the service account. Each service account is associated with public, private RSA key pairs that are used to authenticate to Google. These keys can be Google managed or user managed. Google managed keys, both the public and private keys, are stored by Google, and they are rotated regularly. The maximum usage period is 2 weeks. For user managed keys, the developer owns both public and private keys. They can be used from outside Google Cloud. User managed keys can be managed by the Cloud IAM API, G-Cloud command line tool, or the service accounts page in the Cloud Console. It is possible to create up to 10 key pairs per service account to support key rotation. User managed keys are extremely powerful credentials, and they can represent a security risk if they are not managed correctly. You can limit their use by applying the constraints/IAM.disable service account creation organization policy constraint to projects, folders, or even your entire organization. After applying the constraint, you can enable user managed keys
Let's go to the next video.
Risk caused by unmanaged keys. Consider using Cloud Key Management Service, Cloud Key. In a previous module, we talked about networks, but didn't get into a lot of network security concepts. Let's do that now. First, I recommend removing external IPs to prevent access to machines from outside their network whenever possible. Several options are available for securely communicating with VMs that do not have public IP addresses. These services do not have a public IP address because they are deployed to be consumed by other instances in the project, or maybe through dedicated interconnect options. However, for those instances that do not have an external IP address, it can be a requirement to gain external access, for instance, for updates or patches to be applied. The options for accessing the VMs include a Bastion host for external access to private machines, Identity-Aware Proxy to enable SSH access, or Cloud NAT to provide egress to the internet for internal machines. The diagram on the right shows an external client accessing Compute Engine resources via a Bastion host. The host is behind a firewall where access can be filtered. Whichever method you choose, all internet traffic should terminate at a load balancer, third-party firewall, or API gateway, or through Cloud IAP. That way, internal services cannot be launched and get public IP addresses. Now, VM instances that only have internal IP addresses can use private Google access to access Google services that have external IP addresses. The diagram on the right shows a Compute Engine instance accessing a cloud storage bucket using its internal IP address. Private Google access must be enabled when creating the subnet. You can achieve this either with the G-Cloud command shown here or through the Cloud Console. Regardless of whether your VM instances have public IP addresses, you should always configure firewall rules to control access. By default, ingress on all ports is denied and all egress is allowed. It's your responsibility to define separate rules to allow or deny access to specific instances for specific IP ranges, protocols, and ports. This graphic shows some scenarios where firewall rules can be configured. Egress from Compute Engine to external servers is the first scenario. For ingress, firewall rules should be configured if direct access to an instance is being provided or if via a load balancer. The right-hand graphic shows the scenario of VM instance-to-instance communication. Firewall rules should be considered here to control access also. Remember, you're still responsible for application-level security. If you need to manage APIs, you can use Cloud Endpoints. Endpoints is an API management gateway that helps you develop, deploy, and manage APIs on any Google Cloud backend. It provides functionality to protect and monitor your public APIs, control who has access, using, for example, Auth0, and validate every call with a JSON Web Token signed with a service account private key. Cloud Endpoints also integrates with Identity Platform for authentication. All Google Cloud Service endpoints use HTTPS. I recommend that you use TLS for your service endpoints, and it is your responsibility to configure your service endpoints for TLS. When configuring load balancers, only ever create secure front ends. This dialog shows the configuration of a front end, and the protocol selected is HTTPS, with the certificate also being selected. Google provides infrastructure DDoS support through global load balancers at level 3 and level 4 traffic. If you have enabled CDN, this will also protect backend resources because a DDoS results in a cache hit instead of hitting your resources, as shown on the right. We already mentioned Google Cloud Armor in the networking module. For additional features over the built-in DDoS protection, you can use Google Cloud Armor to create network security policies. For example, you can create allow lists that allow known/required addresses through, and deny lists to block known attackers. This dialog shows a typical security policy configuration where you begin by selecting it as an allow list or a deny list with allow or deny for the rule. If it's a deny, the appropriate action in this example should be a 403 error. In addition to Layer 3 and Layer 4 security, Google Cloud Armor supports Layer 7 application rules. For example, predefined rules are provided for cross-site scripting, XSS, and SQL injection attacks. Google Cloud Armor provides a rules language for filtering request traffic. As an example, consider the first expression on this slide. In IP range, origin.ip, 9.9.9.0/24. In this case, the expression returns true if the origin IP in a request is within the 9.9.9.0/24 range. The second line, request.headers cookie contains 80 equals blah, returns true if the cookie 80 with value blah exists in the request header, and the third line is true if the origin region code is AU. The expressions can be combined logically with logical and or. The expressions are all assigned to an allow or deny rule that is then applied to incoming traffic.
Okay, there's a lot to remember here. Okay, now let's see encryption module. I'm curious what they tell here.
Last but certainly not least, let's go over encryption. Google Cloud encrypts customer data stored at rest by default, with no additional action required from users. A data encryption key, or DEK, using AES 256 symmetric key is used, and the key itself is encrypted by Google using a key encryption key, KEK. This is so that the DEK can be stored local to the encrypted data for fast decryption with no visible performance impact to the user. To protect the KEKs, they are stored in Cloud KMS. The keys are rotated periodically and automatically for added security. This diagram shows a simple App Engine application that uses cloud storage. The data is encrypted using AES 256 using a DEK and decrypted transparently to the application when the data is read. Now, for compliance reasons, you may need to manage your own encryption keys rather than the automatically generated keys, as just discussed. In this scenario, you can use Cloud Key Management Service, or Cloud KMS, to generate what are known as Customer Managed Encryption Keys, CMEK. These keys are stored in Cloud KMS for direct use by cloud services. You can manually create the key using a dialog similar to the one shown here, and specify the rotation frequency, which defaults to 90 days. The keys you create can then be used when creating storage resources such as disks or buckets. When you're required to generate your own encryption key or manage it on premises, Google Cloud supports customer-supplied encryption keys, CSEK. Those keys are kept on premises and not in Google Cloud. The keys are provided as part of API service calls, and Google only keeps the key in memory and uses it to decrypt a single payload or block of returned data. Currently, customer-supplied encryption keys can be used with cloud storage and compute engine. You should also consider the Data Loss Prevention API to protect sensitive data by finding it and redacting it. Cloud DLP provides fast, scalable classification and redaction for sensitive data elements like credit card numbers, names, social security numbers, US and selected international identifier numbers, phone numbers, and Google Cloud credentials. Cloud DLP classifies this data using more than 90 predefined detectors to identify patterns, formats, and checksums, and even understands contextual clues. Some of these are shown on the right. You can optionally redact data as well, using techniques like masking, secure hashing, tokenization, bucketing, and format preserving encryption.
Okay, let's see how hard is the activity. The activity shouldn't be hard. Let's see. So, modeling secure Google Cloud services.
In this design activity, you draw a diagram that depicts your case study's security requirements. Let me show you an example of what to draw. This diagram illustrates a custom VPC network with two subnets in the US. Maybe US Central 1 is our primary region, and US East 1 is our backup region. The firewall rules allow HTTPS ingress from the internal and SSH from known sources. Otherwise, all other incoming traffic is disabled by the implied deny all ingress firewall rule that every VPC network has. Because we're allowing HTTPS from anywhere, it's useful to configure Google Cloud Armor on a global external application load balancer to block any denied IP addresses at the edge of Google Cloud's network. This is a simple design, but a great starting point, because it allows us to grow our backends without changing our security design. Refer to Activity 12 in your workbook to create it.
Okay, so, well, I will not do anything special. We'll just copy it, and let's go through it again because I think it's pretty standard. So HTTP request will arrive to the global application load balancer, where we're going to associate a Cloud Armor block denied IPs, and then a custom VPC will contain firewall rules which will allow only HTTPS calls from whatever IP address, and SSH from only known sources. And the subnet will be active in these regions. Yeah, I mean, in our case will be Europe regions. That's all. We have the implied rules in the custom VPC. That's it.
In this activity, you were asked to draw a diagram depicting the security requirements for your case study. Here's a diagram that I drew for our online travel portal, ClickTravel. This is a similar design to what I showed you earlier. First, I configured Google Cloud Armor on a global external application load balancer to block any denied IP addresses. My custom VPC network has subnets in US Central 1 for my American customers, and a backup subnet in US East 1, and a subnet in Europe West 2 for my European customers. My firewall rules only allow SSH from known sources, and although I allow HTTPS from anywhere, I can always deny IP addresses with Google Cloud Armor at the edge of Google Cloud's network. I also configured Cloud VPN tunnels to securely communicate with my on-premises network for my reporting service. Now, while my load balancer needs a public IP address, I can secure my backend services by creating them without external IP addresses.
Sorry, I want to...
Balancer needs a public IP address, I can secure my backend services by creating them without external IP addresses. In order for those instances to communicate with the Google Cloud database services, I enable private Google access. This enables the inventory, orders, and analytics services traffic to remain private while reducing my networking costs.
Nice. Let's see the quiz. What do they have? 4 questions, 80% minimum. What Google Cloud Service can you use to enforce the principle of least privilege when using Google Cloud? IAM members and roles. What do you have to do to enable encryption when using cloud storage? Nothing, as an encryption is enabled by default. Which Google Cloud features could help reduce the risk of DDoS attacks? Google Cloud Armor. You don't want programmers to have access to production resources. What's the easiest way to do this in Google Cloud? Okay. Use different service accounts for production and development resources with your project. Create a development and production project and don't give developer access to production. Submit. Oh shit. Which Google Cloud features could help reduce the risk of DDoS attacks? But it's not the correct answer. Well, then it will be all of this. This is the correct answer because the simplest way to have separate projects and okay. Let's go forward.
In this module, we covered how to secure our Google Cloud resources. This includes securing both the network and our stored data. We also covered how to secure people using IAM, Cloud Identity, and Identity-Aware Proxy, and how we can secure our applications and machines using service accounts. Remember, security should be put first. Everything else will follow from this.
Sorry, I didn't pass the module quiz. Oh yes, and okay, so retake. What do you have to do? Blah blah blah. Nothing. You don't want programmers use different services? No, created in production. Don't give. Okay. Which? Okay, all of this, and then here we For the principle of list. Okay, submit. Let's see if I understood well. Yeah, nice. We can continue. We'll now mark this as completed.
Secure our Google Cloud resources. This includes securing both the network and our stored data.
Let's go. Now this is the last module, and looks like a quite long one. Therefore, I will have a pause, and I will continue this module in the next video. So see you in the